Okay, let's dive into this. If you work anywhere near the tech world, you've absolutely heard the buzzwords, right? Docker, Kubernetes, containers. But what exactly are they? And why did they basically take over the entire software world overnight? Well, let's figure it out.
So, I have a question for you. What do massive ocean-faring cargo ships and modern software development actually have in common? I know, it sounds like a totally bizarre comparison at first, but trust me, bridging the gap between the physical world of shipping and the digital world of code is literally the best way to build a foundational mental model for what software containers actually do.
Here's the roadmap for today's explainer. We're going to start with a physical shipping analogy to ground us, look at the chaos of the software supply chain, see exactly why containers win, crack open Docker's internal architecture, and finally, map out the newest container trends dominating the industry right now. Let's get to it.
All right, part 1, the physical shipping analogy, moving from bags to boxes. Picture this. For literally thousands of years, transferring goods was an absolute nightmare. It was incredibly tedious. Imagine a farmer bringing loose apples and a winemaker bringing heavy, awkward barrels. Every single type of product was packaged in its own unique way, which meant it had to be manually handled in a highly specific way by sailors. This caused massive friction in the physical supply chain. Loose goods constantly risked being damaged or stolen, and moving cargo from a horse cart to a train to a ship, it required endless manual repacking.
And this brilliantly illustrates the fix, the standardized shipping container. It's really just a metal box, but its dimensions, the length, the width, the height, are globally agreed upon. Shippers never need to unpack the actual goods anymore. To them, the container is just a black box. They don't care what's inside. Because of this uniform shape, the industry could build standardized cranes to load them, standardized trains to move them, and those massive ships to carry them across the ocean. One crane type handles absolutely everything. It drastically reduced friction and just skyrocketed global efficiency.
Moving on to part 2, software supply chain chaos, or as it's lovingly known, dependency hell.
So before containers came along, the software world had its own version of loose apples and awkward barrels. Developers would write an application and just kind of toss it over the wall to operations engineers, who were then expected to magically run it on production servers. But think about enterprise environments. They have dozens of teams writing entirely different apps, all needing to run on the exact same servers. One app might need an older version of a framework, while another needs a newer, totally incompatible version. Operations engineers were left pulling their hair out, trying to balance all these clashing dependencies without completely breaking the server. Installing a single application update could literally require months of planning. It was pure dependency hell, just massive friction in the software supply chain.
Now, the industry's first real attempt to fix this mess was the virtual machine, or VM. The idea was to run a single application on its own, completely isolated VM to avoid those compatibility issues. But here's the catch. VMs are incredibly heavy. They include an entire full-blown operating system like Linux or Windows Server just to run one single app. Going back to our analogy, it's like using an entire massive cargo ship just to transport one single truckload of bananas. It's incredibly wasteful. We desperately needed a new way, something lightweight that perfectly encapsulated the code and all its dependencies.
Which brings us to part 3. Why software containers win. The Holy Grail.
Docker famously coined the phrase build, ship, and run anywhere. And honestly, they hit the nail on the head. A software container acts exactly like that physical shipping container. It bundles the application, the frameworks, the libraries, and all the configurations into one standardized unit. To an operations engineer, it's just a black box. If their server can run one container, it can run any container. It treats all applications exactly the same, regardless of the messy code that's actually inside them.
The benefits here are absolutely massive. First off, developers can simulate production perfectly right on their local laptops. Need a complex Oracle database to test your new code? Boom! You can spin one up in a container on your laptop in seconds, and completely delete it when you're done without leaving a single trace on your hard drive. Second, you get enhanced security. Containers sandbox applications, meaning if something goes wrong in one app, it's heavily isolated from the rest of the system. Operations get way simpler because servers really just need a basic OS and a container runtime. And hey, it's not just for shiny new microservices. Enterprises doing lift and shift migrations of their old clunky legacy apps into containers frequently report 50% or more savings in maintenance overhead. That is a real game changer.
All right, part 4, demystifying Docker's architecture. Let's look under the hood.
Quick terminology check before we get into the weeds here. While Docker is the household name, Docker, the company, actually separated its open-source components from its commercial products a while ago. Enter the Moby project. Moby is an open framework. Think of it as an insider's Lego set of standard components. It allows the open-source community to assemble highly specialized container systems without reinventing the wheel every time, while Docker focuses its commercial efforts on building awesome tools for developers.
So the crucial point is that any host computer running Docker relies on 3 core architectural layers working together. At the absolute foundation, you have the Linux operating system. Sitting above that is the container runtime, which is built from those open Moby Lego blocks we just talked about. And finally, sitting right on top is the Docker engine itself.
Let's break those down. Down at the absolute foundation of the stack is the Linux operating system. Honestly, containers wouldn't even exist without these underlying Linux primitives. We have things called namespaces, which sandbox the processes, ensuring complete isolation. Then we have control groups, or C groups. These limit resources like CPU and memory, which essentially prevents a broken app from hogging all the server's power, fixing what we call the noisy neighbor problem. Moving up to that middle layer, the container runtime, made up of elements like containerd and runc, manages the actual life cycle. It pulls the images, creates them, and runs the containers. Finally, the Docker engine at the very top provides the network libraries, the plugins, and the REST API that actually allows us to automate all of these amazing features.
And finally, Part 5. The new container landscape and post-2022 trends. This ecosystem doesn't sleep. It is incredibly alive and constantly evolving. Since 2022 alone, we've seen a massive shift toward deep, built-in security. For instance, we're seeing huge adoption of tools for generating software bills of materials, or SBOMs, which map exactly what ingredients are inside your container so you can catch vulnerabilities instantly. Technologies like cosign allow for cryptographic image signing so you know for sure a container hasn't been tampered with in transit. On the daily operations side, Kubernetes ephemeral containers are really taking off. This feature lets you attach a temporary debugging container directly to a live pod for real-time troubleshooting without even stopping your app. Docker Desktop has expanded with a really frictionless extensions marketplace, and crucially, rootless Docker modes have finally matured from experimental to stable. This allows administrators to run containers without dangerous root access, which massively drops the security risks.
It's wild to think about how far we've come. We've gone from the digital equivalent of manually hauling loose apples and constantly breaking our servers to hyper-secure, globally standardized, rootless environments that seamlessly scale across the entire cloud. So with built-in security and real-time debugging becoming the new normal, it begs the question, are software containers the final evolution of the software supply chain? Or are we just seeing the very beginning of a completely new computing paradigm? I'll let you ponder that. Thanks for joining me on this explainer, and keep learning.